Today we're going to talk about those applications that required the inverse Z transform, which is what we covered on Friday. So now that we have that as our last tool for working with Z transforms, we're now able to use them for all the different kinds of system analysis and analytical processes that we needed it for. We'll start out just by mentioning and not go through by example, because we did some of those last time, the primary uses of the Z transform that we could do using the two-sided Z transform. That was finding the impulse response of the system. Now that we have Z transforms, we have a simple way to transform the difference equation, rearrange it into a transfer function, and find its inverse transform to find the unit sample response. And in general, even though that sounds like more steps, it typically tends to be an easier and less error-prone process for finding the unit sample response of a system as opposed to doing it by solving the difference equation. Likewise, when we need to find zero state responses for systems, we already know that we can do convolution in the time domain, or we can pick up the problem and move it into the Z domain by taking the Z transform of the input signal, taking the Z transform of the unit sample response, or finding the transfer function of the system. And instead of convolving things, once we're in the transform domain, we simply have to multiply them. And that gives us the transform of our output signal, which by inverse transforms and generally with partial fraction expansion, we can then find the output signal in the time domain. And again, as with finding unit sample response, although that seems like a lot of steps, in general, it's easier mathematically and less error prone than carrying out a convolution in the time domain or trying to solve a difference equation for a zero state response. And in terms of transforms, it's usually simpler to do it with Z transforms than DTFTs because of the fact that the Z transform kind of hides the complex nature of the quantities we're playing with. There's not a lot of e to the j things floating around in our expressions that we have to keep track of. Now, there is one more primary application for the Z transform that was one of our compelling reasons for why we wanted to go to the Z transforms and not just do everything with the Fourier transforms. And that was that there was a class of problems that we could not solve with the Fourier transforms. And it turns out we can't solve them with the two-sided DTFT, or excuse me, two-sided Z transform either. And that was what we were able to do with solving difference equations. We could find not just zero state responses of systems. We didn't have to have our system just relaxed. We could actually find zero input responses and combination total responses that included initial conditions. Once we went to convolution, and when we used Fourier transforms, and when we use two-sided Z transforms, we can only do the linear part of that problem. We can only work with relaxed systems and find zero state responses. But as it turns out, the Z transform has a secondary flavor that is amenable to actually giving us extra terms that we need to handle those initial conditions. And this is very analogous to the Laplace transform, where we had the same kind of situation. So far, we've been using generically the Z transform, and technically speaking, what we've been using is the two-sided Z transform. That's when we transform a time function like h of n, we plugged it into the summation from n equals minus infinity to plus infinity of h of n times z to the minus n. Now, technically, that is the two-sided Z transform. Two-sided because our n could go negative and positive. There is another causal form of that, the one-sided Z transform, where we kick out that lower limit of the summation and begin at n equals 0. Now, for a causal system, finding the transfer function of a causal system, h of n is 0 for n less than 0 anyway. And so the one-sided Z transform captures all the same information that the two-sided one does. We would typically actually shorten the two-sided transform and begin at n equals 0. Likewise, if we had an x of n, a causal signal, if I took its one-sided Z transform, I'm not losing any information. It's just as good as the two-sided transform. And the nice thing about this transform is if both my system is causal and my input signal is causal, the output signal will likewise be causal, but it may have some initial conditions left over from previous inputs. And so this flavor of the Z transform has some unique properties that enable me to account for those previous values of output that may have been present if we had a system that was not relaxed. Now, a lot of the properties of the Z transform are the same for the one-sided and the two-sided transforms. Both are linear transforms. Both we have the convolution of the time domain functions is equivalent to multiplication in the Z domain. Multiplication property, multiplication by n or by an exponential, all those are exactly the same. Doesn't matter whether we're using a one-sided or a two-sided Z transform. We could apply the same properties table if working with the two-sided and the one-sided, with a couple of very important notable exceptions. For scaling, times n, convolution, those ones that we were using to find zero state responses, the one-sided and the two-sided Z transform have all the same properties. So we can do all the same things with the one-sided transform that we can do with the two-sided transform as long as we are working with causal signals and causal systems. The one big difference is the shift property, the time shift property of how a shift in the time domain manifests itself in the Z domain for the one-sided transform. Here, we have to account for the fact that that signal may not have been inherently causal, and therefore when we shift that signal, if we're shifting it particularly to the right, we may have some sample values coming into play that weren't there originally, weren't in the original causal set. Better to describe this by picture. So here's a signal, a y of n, that happens to be non-causal, has non-zero values from n equals -2 to n equals 3. And if I were to take that signal and shift it to the right by 1, delay it by 1, in the two-sided transform, we would say take all of our whole signal and delay it by 1. And we have the expected result for our signal. That would be what would happen if we took the two-sided Z transform and multiplied it by Z to the -1. If we inverse transformed it, we would get the expected signal. If we were using the one-sided transform and our original signal was not inherently causal, wasn't itself one-sided, then if I delay the signal, once I've taken the one-sided Z transform, I'm missing those non-causal parts. All I have in my transform are the parts that started at n equals 0 and went forward in time. Now, if I apply the shift theory to that, well, I'm missing that non-causal sample that was at n equals -1 that's now shifted into n equals 0. Just shifting, applying a Z to the -1 to my one-sided Z transform of my original function will capture most of the appropriate values, but we'll be missing the n equals 0 sample that got shifted in. And so the time shift property, when we shift to the right for the one-sided Z transform, takes this into account and says not only do we have to multiply the Z transform of our one-sided Z transform function by Z to the -1 to get these terms, but in the event that the y of n was not causal to begin with, before the shift, we need to account for that extra sample coming in and becoming part of the shifted signal. So this shift property is different for the one-sided transform, and it becomes recursively applicable. If we have a shift by 1, we multiply y of z by z to the -1 and add in what was at y of -1 now becomes y of 0. If I shift 2 positions, I'm going to take this result, this y of n -1 result, and shift it, so multiply it by z to the -1, giving me z to the -2 y of z plus z to the -1 times y of -1, and bring in the additional shifted in term, y of minus 2. And so however much we delay, we have to account for all those additional samples coming in that shift. Now, the good news for us is that that says that if we apply this one-sided time shift property to our Z transforms, including when we transform the difference equation, we're going to end up with some extra terms that are dependent on previous output values, which are in fact the same thing as my initial condition values. And so we'll have an expression that includes the output in terms of all the other things it used to be in terms of, which included the input and transfer functions and things like that that were part of the zero state response. But now we'll also have terms that include the initial conditions, and it's those extra terms that will give us the missing zero input response piece that we didn't have before. And so the process that we apply is similar to how we were doing zero state responses with transforms, be it DTFTs or Z transforms, but with this new twist. When we take the difference equation and take its Z transform, instead of doing it with a two-sided transform, we'll do it with a one-sided transform. And any delays in that then will generate initial condition terms from any right shifts. Any x of n minus 1s or x of n minus 2s or y of n minus 1s or y of n minus 2s. Each of those will pick up a number, 1 or 2 extra initial condition terms, depending on how big the shifts are. Then we simply continue on with the problem. We rearrange it again, so we have y of z on one side and everything else on the other side, and that gives us the z transform of the output. Now, in terms of the input x of z, or it's the input's transform, but now also including the initial condition terms. Then we just substitute in the known transform of the input, the known initial conditions, and we have y of z numerically in a form that we can partial fraction expand and then inverse transform to find y of n. Now that's too many statements, too many words. We should do an example and see how this works. So first of all, let's try our simplest recursive filter that had a difference equation y of n minus 1/2 y of n minus 1 equals x of n. And we can find the unit sample response, we can find the transfer function, but in this case, we want to work with the difference equation. And we want to know what is the complete response of this system if I put in a unit step input. So what's the total step response? But let's let the system not be relaxed this time. Let's give it an initial condition. Let's make y of minus 1 equal to 10. Now, I have a first order system because my highest order delay in the y side is a 1. First order system needs one initial condition. That initial condition starts at y of minus 1, and we'll say that in this case it's equal to 10. Let's see how the problem would progress using this new method, this one-sided Z transform, to apply this input with this initial condition to this system and predict what's going to come out. What is the total response, including zero input response and zero state response? For that, we'll need to switch over to a whiteboard. So just to keep the problem in front of ourselves, let's write the difference equation again. It was y of n minus 1/2 y of n minus 1 equals x of n. My input was just a unit step input, and my initial conditions, I have 1 at y of minus 1. That was equal to 10. So the first step, we want to Z transform the difference equation. But in this case, now we want to use the one-sided Z transform. So now my y of n, that still transforms as y of z. The term that changes is the minus 1/2 y of n minus 1. We'll carry that minus 1/2 across, but the y of n minus 1 is y of z times z to the minus 1, same as the two-sided transform. But now I pick up that initial condition term, plus y of minus 1. That's the whole one-sided z transform of that particular system. And that equals the z transform of the x, the input signal. So with that now, we can factor out a y of z because we know we're going to want to group that by itself on one side of the equation. So we have a 1 minus 1/2 z to the minus 1. That equals our x sub z. And I'm going to move that minus 1/2 times y of minus 1 over to the other side of the equation so that it becomes a plus 1/2 times y of minus 1. And then simplifying, putting y of z all by itself on the other side, on one side, gives us our x sub z and our 1/2 y of minus 1 in the numerator, and we'll divide that by this term that was with the y of z, minus 1/2 z to the minus 1. And don't like those negative powers of z, so I'm going to multiply the top and bottom by z to the first power so that we have z times x sub z plus 1/2 times z times that y of minus 1 initial condition. And in the denominator, we have a z minus 1/2. Okay. Now we have everything we need. We need to know what x of z is. We know what y of minus 1 is. So we're going to substitute in the z transform of the input, the actual value of the initial condition. And for the z transform of the input, we look up x of z in the table, and the unit step has a z transform of z over z minus 1. So then we have y of z substituting those things in. There's our x of z, z over z minus 1. That's all multiplied by z. And we have 1/2 and a z and our initial condition that was 10. All that is still over z minus 1/2 in the denominator. And so these two together are going to give me a z squared in the numerator. I'm going to have to take this down to the denominator, which means I'll need to multiply this term by that as well. The 1/2 times 10 is going to give me a 5z times z minus 1. In the denominator, I now have z minus 1 and z minus 1/2. So just manipulating things algebraically or simplifying. This is a 6z squared minus 5z in the numerator, and in the denominator, we can keep our two terms still separate if we like. And we have the z transform of the output. The rest is just partial fractions to get us back to the time domain. But of course, we need to partial fraction not y of z, but y of z over z. which is then just 6z minus 5 in the numerator, and our two terms in the denominator. Z minus 1/2 times z minus 1. And we partial fraction expand that into two terms. One that goes with the z minus 1/2 term, we'll call that A. B that goes with the z minus 1 term. And if we do a little partial fraction magic over here, our A is 6z minus 5 over z minus 1, evaluated at z equals plus 1/2. When we plug in those values, we see that it's 4. B is 6z minus 5 over the opposite term in the denominator, z minus 1/2, evaluated at z equals plus 1. That comes out to be 2. And so we have A equals 4, we have B equals 2, and our y of n then, let's put in the green thing we're looking for, y of n, the inverse transform of 4 over z minus 1/2, well, that's our y of z over z. Our y of z then equals 4z over z minus 1/2, and 2z over z minus 1. That we can inverse transform directly using lookup table. That's a 4 times 1/2 to the n u of n, and 2 times z over z minus 1 gives us a 2u of n. And that is the total response. That's the zero state response and the zero input response together, all solved at simultaneously, not separately. And in fact, we can identify, we put in a unit step, we got out a 2-unit step, the same basic form. So there's our forced response. And the pole, the z minus 1/2 that created this 1/2 to the n u of n, came from the left side of the equation. The y side came from the characteristic equation. And so that then must be the natural response. So what was different if we had been solving just a zero state response? We wouldn't have had this term. We wouldn't have had this term. We wouldn't have had this term. We would have still gotten something that had both these terms in them, but we'd get a different natural response. Probably we would get the same forced response. This would have been, we see our x of z, the z over z minus 1/2 would have been our transfer function h of z, because we wouldn't have had this piece. And so the initial condition part that we picked up came from those initial condition terms came along as part of the shift property of the one-sided z transform. And if we evaluated this expression that we got for y of n for different values of n, now let's do that. Let's make a little table here of y and n values and y of n. We plug in n equals 0, you get 4 times 1/2 to the 0, which is 1, times a 1, plus 2 times 1. So it looks like we would get 6 for that. For n equals 1, we would get 4 times 1/2, which is 2, added to 2, giving us 4. For n equals 2, we would get 1/2 squared, which is a quarter, times 4, which is 1. plus 2 gives us 3. And just to round out, if we put 3 in, we actually would get 2.5. And if we look at what happens as n gets really, really, really big, as n goes towards infinity, well, in these terms, this 1/2 to the n becomes tiny, becomes minuscule. So this term no longer contributes. We're left just with this constant 2. And so as this tends towards infinity, we tend towards a value of steady state value of 2. And if we had run the difference equation and plugged in a unit step with the initial condition of 10 in a recursion table, we should and we would get these exact same values out as well. It should give us the same answer. So that's how we apply this time shift property of the one-sided Z-transform. That again, if we have a causal signal and we're applying it to a causal system, we can do it without any loss of information. We pick up these extra terms, and they give us the ability to find the zero input response. If I had just wanted the zero input response, let's clear a little space and see how we would have addressed that. If we were finding a zero input response instead, then we would have still transformed our difference equation the same way. So we'd have an entry exactly like that, but the zero input response, the difference is the zero input response is the response of the system for zero input, literally, which means I would set this input equal to 0 and would have gotten a very different response. I would have gotten just the part that was due to those initial conditions. We've taken our y of z, add to 1 minus 1/2 z to the minus 1. That now equals to 1/2 y of minus 1, bringing that term to the other side. And this we know is a 10, so it's actually equal to 5. So we have that y of z is 5 over 1 minus 1/2 z to the minus 1. And if we multiply top and bottom by z, that's 5z over z minus 1/2. That's simple to inverse transform. That's simply 5 times 1/2 to the n u of n. Now, previously, when we did the total response, let's be clear, let's put the ZIR in there. That's the zero input response. When we had the total response, we said that that was four times 1/2 to the n u of n plus 2 times u of n. So guess what? We know that the zero state response, which should be the difference between those, is a minus 1 times 1/2 to the n u of n plus 2 u of n. So that the zero state response plus the zero input response gives me the total response. And this is what we would have gotten if we had solved the problem with the two-sided transform. If we'd done it in the y of z equals x of z times h of z methodology. Should all be consistent. So why are we doing this? Well, again, this approach of finding the total response using these z transforms is, although the transforms add steps to it, it's actually mathematically easier than trying to do this in the time domain, compared to trying to do an analytical convolution, or compared to trying to solve a difference equation for a particular set of initial conditions and particular input signal. We don't have to worry about generalizing zero state responses. We don't have to worry about any special cases that might occur that we have to watch out for and change our assumptions. of forced response or natural response shapes when we're solving the difference equation. All of that is handled for us in the algebra of the Z transform. We can just carry through the process in a very straightforward manner, and the forward and inverse transforms will handle any of those special case things that may pop up. So this makes it much less prone to problems. You'll notice we've solved the whole problem on basically one board, which would have required several pages to do if we were solving with difference equations or doing a convolution. And so typically this is a much better way to do things. This is why we introduce transforms. Just as Laplace was the better way to solve linear constant coefficient differential equations, using the Z transforms are probably the better way to solve linear constant coefficient difference equations. There are two additional theorems that are worth mentioning before we move on from Z transforms. They are theorems that will give us a quick way to predict the initial or final value of the time domain function if we have their Z transform. The initial value theorem says if you want to know what is the beginning sample value at n equals 0 for a causal signal that's starting there at n equals 0, take its one-sided Z transform x of z and take the limit as z goes to infinity. Similarly, if we want to know what is the steady state value of our time signal, what's the value of x as n tends towards infinity, if we have its Z transform, well, we take the Z transform one-sided or two-sided, multiply it by the quantity z minus 1, and then evaluate that quantity as z goes to 1. Let's see that in practice with our previous example there. For our recursive filter with a unit step input and initial condition of minus 10, we derived this Z transform for the total response of the system that included zero input and zero state response, and ultimately came up with this y of n, this output for the total output response in the time domain. Now, according to the initial value theorem, if I want to know what was the output here at n equals 0, and I have the transform available to me, I just substitute in and take the limit as z goes to infinity in my y of z. And so that would be the limit as z goes to infinity of either of these two forms, with or without the factored denominator. And, well, we can't have the positive powers of z, so we divide the top and bottom by the highest power of z, which is z squared. And we get 6 minus 5 z to the minus 1 over 1 minus 1.5 z to the minus 1 plus 1/2 z to the minus 2 using the unfactored form. Now we can take the limit as z goes to infinity. These z to the minus 1s are 1 over z's, so as z goes to infinity, those go to 0. So all these terms except the 6 in the numerator and the 1 in the denominator go to 0. So I'm left with an initial value of 6, which if we plugged in n equals 0 to our difference, or not to our difference, to our total response equation, we would get the same value, 6. Likewise, the final value theorem says if we want to know what is y of n as n goes to infinity, we would take our Z transform, multiply it by z minus 1, and then take the limit as z goes to 1. If we use this factored form, when we multiply by z minus 1, the factor in the numerator and denominator cancel. We're left with 6z squared minus 5z in the numerator, z minus 1/2 in the denominator. And let z go to 1, we get 6 minus 5, or 1 in the numerator, 1 minus 1/2, or 1/2 in the denominator, giving us a value of 2, which is what we derived and said if n as n goes to infinity in our result, the 1/2 to the n goes away. We're left with just the 2u of n. So 2 is in fact the final value. So we see how we can use the Z transforms to give us a quick answer, if we have those available to us, to the initial and final values of a causal signal. Okay. With a couple minutes remaining, this method of finding the total response is really what the course is all about. And so we've introduced to you a number of ways of doing it, starting in the time domain, starting with solving difference equations, moving on to learning convolution, taking that convolution to find zero state responses into the frequency domain with the DTFTs, then transferring it into the Z domain to deal with more problems. And now finally getting back to where we could do everything we could do with difference equations in the Z domain with the one-sided Z transform. So now we can handle any kind of problem if we have a linear constant coefficient difference equation representing a linear time invariant system. You give me an input, I can tell you what comes out of that system as long as you tell me what the initial conditions were. So it's worth practicing this a little more. Again, all of homework 7 is a number of different practices on that. Please do try those, but let's take one additional example here that adds one additional twist by adding a delay on the X side, so we see how to handle that, and we can take this forward pretty quickly to a complete solution. So if we have this difference equation, let's put in not a simple unit step, but let's put an exponential input in. One that's 2 times 4/10 to the n u of n. And let's start with an initial condition. Again, still just a first order system. So y of -1 is the only initial condition we have, and we'll set that equal to +5. And the question is, what's the total response of this system to this input if it started with this initial condition? Well, let's go check it out. Back to the whiteboard. And let's write our problem up here again. The difference equation, y of n minus 0.4, y of n minus 1 equals x of n minus 1/2 x of n minus 1. And our input, x of n, was 2 times 0.4 to the n, a causal signal, and our initial condition, y of -1, is equal to +5. So first we take the one-sided Z transform of our difference equation, y of z minus 0.4 times the quantity of z to the -1 times y of z plus y of -1 for that time shift equals x of z minus 1/2. And we have an x of n minus 1, so we'll apply the theorem to that as well. Z to the -1 x of z plus x of -1. So this is the new twist we have here, this x of -1 that we didn't have before. And what do we do with that? Well, not so much of a problem as you may think, because x of n is a causal signal. And so by definition, x of n equals 0 for n less than 0. And so we can actually ignore that term. That sends us back to the problems, makes it similar to what we had before. We factor out the y of z, becomes a 1 minus 0.4 z to the -1. We have a minus 0.4 y of -1 on that side. We have x of z on this side. And we have a 1 minus 1/2 z to the -1, but I don't have that initial condition on the x term anymore. We want to bring y on one side by itself. So we'll have our x of z times the factor that was on the left side with it. We'll add the 0.4 times y of minus 1 over to the left side of the equation, and we'll divide everything by that term that's multiplying the y of z up above, 1 minus 0.4 c to the minus 1. And again, not real pleased with all those negative powers of z, so I'll multiply by the first power of z and have x of z times z minus a half and 0.4 times z times our y of minus 1 divided by z minus 0.4. We have our initial condition. We know what that is. That's a 5. We need our x of z, the z transform of our input. Well, we're going to definitely have the 2, and the 0.4 to the n u of n has a transform that should look like z over z minus 0.4. And so we can substitute all that in. Our 2z over z minus 0.4 for our x of z times z minus 1/2 in the numerator plus 0.4 z times our 5 from the initial condition, all divided by z minus 0.4. And we get to simplifying. Now I've got a z minus 0.4 here. I'm going to end up having that, moving that down to the denominator, leaving me with, looks like, 2z times z minus a half in the numerator, plus this 0.4 times 5 gives me 2 times the z we had here times this denominator, 2 minus 0.4. Now over the quantity z minus 0.4 quantity squared. So we're combining another common denominator, which simplifies to 4z squared minus 1.8z over z minus 0.4 quantity squared. Now there's several different ways to attack this. We've got the z transform of the output. The most straightforward way would be to do a partial fraction expansion on y of z over z, which happens to be 4z minus 1.8 over our denominator squared. That's a second order repeated root, repeated pole, so we're going to need a A0 term with that whole thing. And we're going to have a first order term with it to the first power. And if you were to plug in and find those partial fractions, we'd find that A0 happens to end up being minus 0.2, and A1 turns out to be 4. So then our y of z, the thing we're going to inverse transform, is minus 0.2 times z over z minus 0.4. That was with the quantity squared, plus 4z over z minus 0.4. And looking that up, our y of n, then the inverse transform of that, just to show you all the terms, we'll get a 0.2, we'll get a minus 0.2. We're going to need a 1 over alpha in there. then n times 0.4 to the n u of n. That's the inverse transform of this first term. And this term gives us a 4 times 0.4 to the n u of n. That's the total response of the system, including zero input response and zero state response. Now, two things to note here. One was when we had delays on the x side, if our input is causal by definition, any delay terms that come out of those one-sided z transforms of the right side of the difference equation, we just set those initial values equal to 0. The other thing to notice is that if we were solving this equation by solving difference equations, this would have been one of those special cases that we would have to worry about, where our input signal had the same form as the natural response of the system, or its form matched one of the roots of the characteristic equation of the system. In that case, we had to make a different assumption about our forced response, and we would have had to solve the problem differently. We didn't need to notice that when we used z-transforms. It all just fell out of the algebra by itself. It led to this n times result that we had here with the repeated root. The repeated pole down here was caused by it, and we dealt with it in the inverse transform and in the partial fraction expansion. So the method doesn't change for any of those special cases. It all just falls out of the algebra. So that's a real nice advantage of doing these with the z-transforms, and why we come to the z-transforms to do it. And with that, we end our coverage of z-transforms. You now have a complete set of tools to do system analysis. As I said, next week we want to come back after the exam, learn about the discrete Fourier transform, and expand our horizons on the kinds of signal processing that we can do, and see how it's done by computer systems where we have to have transforms that are discrete, just like our time domain discrete sample values. But with this, though, we have the complete z-transform tool set. Please practice that up for homework. Please make your preparations for the exam that's coming up, and we'll see you then.